Hello and welcome to this presentation about Meadow, a NuttX powered .NET development system. My name is Mark Stevens and I'm a firmware engineer working on the Meadow platform. I've been a software engineer in the past, project manager, operations manager, and a few years ago went back into software development and started working on the firmware for the Meadow boards. I've been playing around with hardware and software since the late 1970s, and this has been an interesting challenge for me. So in this presentation, we'll have a look at Meadow. We'll get some background on what Meadow is, both the hardware and the software. We'll have a look at .NET and managed applications and the history of these platforms in the microcontroller space. We'll then have a quick look at the architecture for the board and the software. Then we'll take a dive into some of the details to see how NuttX is used and the features we've used, the challenges we've had, and we'll finish with a look at what the future holds for Meadow. So let's start off by having a look at the boards and the software platforms themselves. So at the moment we have two boards. Meadow only runs on these two platforms at the moment. We have the F7 Feather board, which is the board on the left hand side, and that uses the Feather form factor, which anybody who's had a look at some of the more modern Adafruit boards will be familiar with. We use the same pinout with a couple of additional pins at the bottom to give us a few extra IOs, a few extra features. The board on the right there is the core compute module. This has a larger number of GPIO pins. It's also capable of talking to Ethernet controllers and SD card interfaces. Both boards have two microcontrollers on them. They have an STM32 microcontroller as well as an ESP32. They're quite powerful in terms of the amount of memory they have available. So we have 64 meg of flash for application and data storage. We also have 16 megabytes of RAM for use when you're running the applications. Of the 64 megabytes of flash, we do actually need to reserve some space for operating system requirements, but you do end up with somewhere in the region of about 60 megabytes of space available to you. As you would expect from an embedded development board, we have a wide range of GPIOs available to you. So we have all the usual suspects. So we have digital input-output, analog inputs, SPI, I2C, we have UARTs available to you, and I2S, as well as CAN and DAC available. So let's have a look at .NET and how .NET fits into the embedded workspace. So a little bit of the history around .NET as well as the current frameworks that are available. So on a microcontroller, in the microcontroller space, .NET really started out or became popular with the .NET Micro framework. This was absorbed a few years ago, and a group of people took it on and created the Nano framework. So the Nano framework runs on a range of microcontrollers of various capacities and various power. It is unfortunately at the moment a .NET 2 based platform, and for those who have been following .NET, we are now running, I think we're getting ready for .NET 7. I think that's in release candidate at the moment. Application development is also restricted to C#. Then if we have a look at the Raspberry Pi, so not a microcontroller but a single board computer, you do have full .NET available to you. You can develop in a language of your choice, C#, F#, VB. And because it's not a microcontroller, you get a higher power consumption because you're running a full operating system on a single board computer. There's also Tiny CLR. This is available but without things like generics in the language, and it's limited to the number of assemblies and assembly sizes that you can use. And finally, we come to the product we're talking about today, which is Meadow. So this is .NET Standard 2.1 and .NET 6 is planned with, obviously when .NET 7 comes available, we'll have a look at that. Like the Raspberry Pi, you have a choice of programming languages, so you can use C#, F#, or VB.NET. You can also, because it's .NET Standard 2.1, use a wide number of libraries available through NuGet. We also provide a number of libraries to support access to the peripherals that are available on the board. The Meadow Hardware has built-in Wi-Fi and Bluetooth. This is available through the ESP32 microcontroller, and we'll have a look at that a little bit in more detail a little bit later on. The Meadow boards are designed to be managed by cloud, so application updates, security updates, operating system, etc., all available through over-the-air updates from a cloud management platform. And the Meadow board uses two microcontrollers, the STM32, which is our main controller running the .NET platform, and the ESP32 providing access to Bluetooth and Wi-Fi. So similar to Nano framework and similar to Tiny CLR, we're available on low power platforms. So just to understand some of the benefits of .NET software development for those who aren't aware or haven't used .NET, we have a variety of modern languages. So we can use C#, F#, VB.NET. This compares to more traditional microcontroller development using C or C++. In this platform, the memory is managed by the runtime system. This makes it more difficult to have memory leaks or to overwrite the bounds of memory that you've requested. So as a result, this becomes a safer development platform. You have access to a number of modern tools. So we have Visual Studios on both Windows and Mac. VS Code is available on Windows, Mac, and Linux. And from the last statement, you must be able to gather that we have a choice of operating systems available to you. As I say, you can develop on Windows, Mac, or Linux. It's up to you. It's your choice. And also, with it being .NET, there are a wide number of libraries available to you through NuGet, as well as additional libraries that we are providing to access various peripherals, and also extra development boards, such as barometric sensors, so you can do humidity, air temperature, air pressure, etc. Debugging is available through the IDEs. So we're using modern IDEs, Visual Studio on Windows and Mac, and Visual Studio Code on all three platforms. Because the Visual Studio and Visual Studio Code don't know about the Meadow platform, we need to install an extension in order to connect to the hardware. But once that's installed, you have full access to the board itself. And unlike traditional C development, where you quite often need an external debug interface, such as a JTAG adapter or SWD, ST-Link, etc., access to debugging on the Meadow boards is through a single USB connection direct through to your Mac. No additional hardware is required. And as you would expect, if you're debugging an application, you need access to things like single stepping, breakpoints, variable inspection, and these are all available through the IDE. So now we've got some background. Let's have a look at the architecture for the hardware and the software before we go into a deep dive. So as we mentioned earlier, we have two microcontrollers on the board. We have an STM32F7 with 2 megabytes of flash, 512 meg of RAM built into the chip, and it's running at around about 200 megahertz. The STM32 talks directly to 16 megabytes of RAM available to the user application and also to the runtime system. We also have 64 megabytes of flash, of which around 60 megabytes is available for data storage and the application. The STM32 itself provides direct access to the various I/O features that we saw on the previous slide. On the core compute module, we also have access to an Ethernet interface, and this is native through one of the drivers built into NuttX, which we'll see later. We also have access to the SD card interface, again through NuttX. Wi-Fi and Bluetooth wireless is provided through the ESP32, and this is a Pico D4. This has 4 megabytes of flash built into the system. We have about 520 kilobytes of RAM available for data storage and for instruction storage. I think this becomes about 180 kilobytes by the time that the system started up and the application is loaded. This chip runs at a quite beefy 248 megahertz. And is connected direct to the STM32 in order to provide the Wi-Fi and the Bluetooth features. And we'll have a look at how that's achieved in a later slide. In terms of the software, the managed code, the .NET application, is all running on the STM32. So at the top of the stack we have the user application. This is running, as we mentioned, C#, F#, or VB.NET. Then we have two groups of libraries sitting under the application supporting it. So the first is the standard .NET libraries. So this provides access to various features such as writing to the console, so we get user output, or managing memory, so allocating memory for, say, a dictionary to hold data values and so on. Then the other set of libraries are provided by Wilderness Labs, and they are the Meadow libraries. And these fall into a couple of categories. The first are to support generic features such as GPIO, SPI, I2C, etc. And the second group is the peripheral libraries, which encapsulates the features provided by something, say, like a BME 280 atmospheric sensor. All of these are supported by Mono. So Mono actually takes the user application, works out what libraries are needed, and starts running through the various libraries and supports running the application itself. So all of these components are currently running in managed land. Now Mono itself isn't running on a .NET operating system. It's running on an operating system that's running written in C or C++. So it needs a way of communicating with that native code. So the first thing that we hit is the platform abstraction layer. And at the top of this layer are the features that Mono is expecting. And then underneath that there is a series of API calls which will call into the native system. Now in our case this is NuttX. And as NuttX is exposing a POSIX API, the platform abstraction layer that sits above it is using that API, so is linked through to a Unix type abstraction layer. So the POSIX features things like reading from a file, reading a socket, creating a socket, and so on. These calls are made from the bottom of the abstraction layer through to NuttX, and then NuttX works out how to provide those features either through, say, a native Ethernet interface, or in the case of Wi-Fi, through the code that we have written to support talking to the ESP32. So if we have a look at the ESP32 itself, we chose to use FreeRTOS on the ESP32 as that was available at the time, and it's fully supported by Espressif. And then sitting on top of that are various tasks which run to support Wi-Fi, Bluetooth, and some things that we have categorized as systems, so things like power management and so on. So now we've got an overview of how the system it looks from an architecture point of view, let's start to have a look at some of the details of how the system is laid out, the features that we've used, and how they are interacting together. So within NuttX itself, we are using the kernel protected build of NuttX. So we have two user applications which are running on the board, as well as the kernel itself. So we have the USB communication interface. This allows us to talk to a PC, a Mac, and so on. And it does this by exposing USB over serial over USB. Now the USB communication provides a number of features. So we do things like device controls. So do we actually allow the application to run? Are we taking information from the user application and providing that back to the user? Another thing we do is we allow deployment of an application or the operating system itself, both from a PC direct through to the board. And the other feature that we provide is debugging through a socket interface. So in this case with debugging, we are taking commands from an IDE through the serial port on the PC, which ends up in the USB communication interface, and that talks to Mono, and Mono controls running of the application and provides features such as variable inspection, single stepping, and so on. Okay. So let's have a look at networking and Wi-Fi. So as we discussed earlier, Mono is using the Unix platform abstraction layer, and that ends up in a series of POSIX calls for operating system interaction. So in our case, these POSIX calls end up in the NuttX operating system. And remember that the NuttX in this case at this level is running as in a protected mode kernel build. So we need a way to have NuttX talk to FreeRTOS, and this is done through the SPI communication interface, which connects the two chips together, or just one of the SPI interfaces that are available on the STM32. So FreeRTOS itself is multi-threaded, and by chance it also happens to expose a POSIX network API. So we can use the SPI interface to send the POSIX request that NuttX has received through to FreeRTOS for it to implement those POSIX or make those POSIX API calls for us. So the challenges we have in this space, firstly, NuttX is multitasking, as are .NET applications. They have the possibility of being multitasking. So we don't know when an API comes through to NuttX, we don't know which task that has come from. So we need to find a way of making sure that when a request is made from, say, a multitasking .NET application, that the correct response goes back to the correct task. And this is complicated by the fact that we have a single SPI bus that's connecting the two chips together. So this means we have a multi-threaded system hitting a single SPI interface, and we can only have one set of messages going through that interface at any time. There's also another complication because the ESP32 itself, the SPI chip, the SPI interface has a known limitation that you can only send 4092 bytes through that interface, and that is 4092, not 4K as in 4096. So we have those that to take into consideration as well, bearing in mind that the user application could be requesting, say, 10K across the internet. So we need to work out how to work with that 4092 byte requirement. So from a Wi-Fi perspective, we've got a number of challenges. We have the multi-threaded challenge. We also have the challenge that we have both Bluetooth and power management for the ESP32 working alongside Wi-Fi. We have the synchronous SPI interface, so we can only have one message at a time being sent, and also we need one of the chips to be in control of the interface, and in this case we've chosen the STM32. We also have have a problem we need to consider, that the Wi-Fi could disconnect, or we get connection events, we get disconnection events. Disconnections we have no control over when they happen. So we need some way of getting those events from the ESP32 back to the STM32. And from the STM32 perspective, we provided support for two different types of methods, and we've called those methods blocking and non-blocking. So if you take something like a receive from or a send to POSIX API call, they are blocking messages in that when we generate the message that we send over, or when we generate the request from the platform abstraction layer, Mono itself is expecting to wait until a response is received. It's not expecting a response to be generated at some point in the future and then to be notified of it. And that brings us on to the second message types, which are non-blocking. So we could fire off from, say, the .NET application. We could say, I'll connect to the Wi-Fi interface, do it non-blocking, and just let me know when the connection's been made. So in that case, we would send a request from the user application through the .NET libraries that we have into NuttX to the ESP32 to say, connect to the Wi-Fi, raise an event when it's done. And when that request has got to the bottom layer and into NuttX and it's been passed over to the ESP32, we will immediately return so the user application can carry on working. So let's have a look at this in action, and we will use the case of the receive from. So this method assumes that we have a socket connection already established. The method, the caller is expected to provide a buffer to hold the data that it wants, along with an indication as to how much data the application is expecting back from the network. So let's have a look at this in action. So the first thing that is going to happen is that the receive from method inside NuttX is going to work out which network interface this is intended for. And in order to do that, we're using the PSOC interface, and we have defined a group of tables inside a table which contains a group of methods that implement effectively some of the user SOC calls. So we're partially using the user SOC interface. Now, in order to make sure that this is a blocking call, remember we're trying to keep both NuttX and the ESP32 working in a non-blocking manner and running in a multi-threaded system. We need a way of blocking the message, blocking the request once it's been made. And to do that, we add a semaphore to the request itself. So the PSOC interface, the call that we've implemented, it wraps all of the request plus the semaphore into what we're calling a message. And that message, in order to make sure that we can identify both the source of the message and also where we need to send the response back to, we also have a message identifier added to the message. Also, any payload, a payload by any data that is needed to support the request is also encoded in what we call a payload. So in the case of a receive from, the three basic pieces of information that are always used are the socket number the request is intended for, the buffer to hold the data, and the size. Now, in this case, when we're sending the message across to the ESP32, we don't need the buffer. The ESP32 doesn't need the buffer because it doesn't matter what's in there at the moment. It's when we get the response back, we will need to copy the data from the ESP32 response into the receive from buffer. So we don't need to send the buffer across. So we just need to send things like the socket handle and the amount of data that's required. So we wrap all that up into a message, and the message has an associated payload. So the next step, we need to get that over to the ESP32. So within NuttX, we have a thread that is running, and its sole responsibility is to monitor the message queue. And when a request comes through from the message queue, the thread picks this up and it then starts working out how to send that to the ESP32. As we've mentioned before, this connection is through an SPI, but we also have the case where we have a response that's required. So another thing that the SPI thread has to do is it has to keep a record of the messages which we're waiting for responses for. So in this case, PSOC, we've created a semaphore because it's a blocking message. So once the SPI thread has received that, part of the process is to keep a list or keep a record of the messages which we're waiting for a response. Once we've added that message to the waiting queue, as in waiting for responses, we can then send the message over SPI through to the ESP32. Similar to NuttX, the ESP32 runs an SPI task, and its sole responsibility is to monitor the SPI bus, follow the instructions from the STM32, and in this case the instruction is going to be, here is a receive from request. So similar to the STM32, we have some message queues on the ESP32. So in this case, the request is a receive from. It's a Wi-Fi request. So step 3 is to add the Wi-Fi request through to the Wi-Fi queue. And again, these are messages in the same format as they were generated on the STM32 within the NuttX user SOC driver. We also have a group of tasks running on the ESP32, and one of the tasks is the Wi-Fi task. And its main responsibility is to monitor the Wi-Fi queue, and when messages come through for the Wi-Fi system, it takes those messages from the Wi-Fi queue, implements the functionality that's required, and in this case it's a receive from, and then it works out the response, the response from the network. So in this case, if everything goes well, we will have a buffer which contains the data that was requested by the STM32 by NuttX. So we take all of the response, and then we package this back up as another message. And the Wi-Fi task then puts this response message into the response queue. And just as you would expect, there's a task whose responsibility is to monitor the response queue. And when it sees a new message turn up in the queue, it then sends an indication, not over SPI this time, but over GPIO, to a task listening on the STM32 to say, I need your attention. So the listener task on the STM32 now has to work out how to get the response back from the ESP32, and the obvious way to do that is to put a special message into the message queue. And this message is to say, look, the ESP32 has something for us. This could be a response from a previous request, or it could be an event such as a Wi-Fi disconnect. So this message goes in the message queue, and the SPI thread, through the same interface as we sent the response through to, the original request through to the ESP32, can then say to the ESP32, I believe you've got some information for me. So the SPI task on the ESP32 receives this, and it retrieves the response from the response queue. So we've now completed the loop, as the STM can now get the response back. It can look up the response in the list of waiting messages, find out where the message request came from, and it can then put the response from the ESP into the original message and then trigger the semaphore, and that completes the loop back to the original PSOC received from request. So this slide is just there to aid anyone who downloads the presentation, and it effectively runs through all of the stages on the previous slides that we've run through. So this leaves us with a few challenges. We have to work out how to do the initial synchronization of the two systems in the first place, because obviously NuttX is starting up at a different speed than the free RTOS. So we need to synchronize those two possibilities, those two chips. We also have the possibility that we could get noise interfering with the data that's transmitted on the SPI bus. We could also get noise on the interrupt line between that's indicating that the ESP32 wants some attention. As we've noted that the STM32 code, both NuttX and the user application, are both multitasking. So we need to take care of message sequencing. Because we could end up with a request to a slow server on the internet, which comes in followed by a request to a fast server on the internet, and we need to make sure that those two messages are dealt with as fast as possible, and that the right caller gets the right data. As noted, we have a message size restriction imposed on us by the ESP32, so we need to work out how do we overcome that. So we've implemented multi-packet messaging, so if the user application wants 10K worth of data, then we can, through the multi-packet interface, we can break that initial request down into, or the initial request and the response down into multiple packets. So if there is 10K of data available, then the user gets 10K back. We also have problems with timeouts. And again, this is partially to do with synchronization of the two chips. So we could have an SPI request go over to the ESP32, and we could have an issue on the ESP32 where it's busy with a particular task and it misses the messages. So we have to take all those scenarios into consideration in order to provide a secure and guaranteed message transmission system between the two chips. So some of the other challenges that we've come across. The scale of the problem. So if you have a look at the specs for the hardware, if you remember, we have 16 megabytes of RAM and 64 megabytes of flash. And for a microcontroller development environment, that's quite beefy. And all that's required to support .NET and getting it running on a modern microcontroller. Our current software version, we've got a relatively old version of NuttX. We do have plans to rebase in the future sometime when we get to version 1. But occasionally we hit an issue that's already been solved. Or we hit a particular feature call from Mono that's been implemented in, say, in NuttX 10.2, but we haven't got that feature in our system yet. So we have to occasionally pick and choose. We may take a full file from the current release, which I've done recently, or we may just take an element out of a switch statement, which again I've done recently, just to get a particular part of the system working. As I say, the plans are to, at some point in the future, to actually rebase, and to also rebase a little bit more frequently to keep us more up to date. We also have, as noted, the errata with the ESP32. This caused us a few challenges initially. But once we worked out what the problem was, it was relatively easy to work around. It was just working out what the problem was. The USB communication, we originally implemented that as a kernel mode module. And in the early stages of development, as you can imagine, when you're developing early on, we get the occasional crash in the comms software. And this would occasionally bring the operating system down, which is why it's now a user application. We should have done that originally, hindsight, but it's in the right place now. Some of the heaps, some of the testing is challenging in a multi-threaded environment. We have some challenges with heap checks. In particular, so we would fire off a request to the ESP32 for it to pull back a web page, and because of the nature of the system, the memory for the messages that are transmitted between the two chips might be released slightly after we return to the test code, which makes things a little bit interesting when you're trying to compare the heap before a request to the heap afterwards to make sure that you're not leaking memory. One of the future things, or one of the key components of the system, which is currently in flight at the moment, is updating the system. So we have over-the-air updates. And these aren't just over-the-air updates for one particular piece of the system. We have the user application to consider. We have the Mono runtime environment to consider, as well as NuttX and the code running on the ESP32. And it's essential that we get all these things synchronized with the right versions in the right place in order to ensure that all of the components can work smoothly together. So what does the future bring? So we're heading towards release 1. Somewhere after release 1, we need to do a look at a rebase of NuttX. We also have to look at things like .NET Core, so looking at the new releases of .NET. We also have dynamic linking in flight, and if you have the chance, a colleague of mine, Neil Ferguson, who is also working on the project, has a presentation regarding dynamic linking, and that is going to be presented during this workshop. One of the other things we plan to implement is ahead of time compilation. So at the moment, all of the user application is either run through an interpreter or is run through a just-in-time compiler. And that compiles the application down to an intermediate language, which is then interpreted by the Mono runtime system. Now, as you can imagine, there is an overhead associated with that. So one feature to be implemented is a head-of-time compilation, where the user's application will be compiled down to native instructions on the PC, and that native binary will then be uploaded onto the microcontroller. So this should hopefully achieve a few things. One is to reduce the size of the application and the memory footprint required, but also give us a little bit more of a speed boost for the user's application and for the system. So that's what the future holds. If you want more information, we have a presence we as in Wilderness Labs has a presence on the internet. A lot of our code and hardware designs are available through GitHub. We're regularly tweeting. We also have a number of projects on Hackster.io which show how the system and the various libraries connecting to peripherals and so on work, and we also post on YouTube and Twitch on a regular basis. Myself, I'm also available through Twitter. I have a blog where I document what I'm doing in terms of electronics development or software development, and I'm also available on LinkedIn. So thank you very much for your time, and we'll open the floor up to questions.